Wonderful. Great. Thanks very much. Good morning, everyone. My name is Josh Bongard. I'm a computer science faculty member here at the University of Vermont. And what I wanted to do this morning is not to talk about any particular software package, but I wanted to talk about one of the challenges that we all face in the soft robotics community, which is simulating dynamics that occur across very different temporal scales, very different time scales. At the moment, in robotics, obviously our machines and ourselves, we have to grapple with the external world, and the world itself changes at many, many different time scales. And my empty outline here of the Asimo robot, not to pick on Asimo, is that in traditional robotics and rigid robotics, if you look inside the machine, there is no adaptation, there's little change, and there is obviously little change across timescales. If we look at organisms, on the other hand, we see that organisms have very rich inner lives. There are adaptive processes unfolding all the way from the picoscale up to large-scale body development, which unfolds over decades and in some species even centuries. So we see adaptive processes unfolding at very different timescales that are missing from traditional robotics. In my plenary talk on Wednesday morning, I'm going to talk a little bit more about this lack of a rich inner life in our robotics, but I think this is one of the promises for soft robotics. As our ability to manipulate exotic materials improves, we can create machines that do have rich inner lives, and that can be useful in grappling with the outside world. Going back to organisms for a moment, we have rich inner lives, including rich inner mental lives. So I thought it would be particularly appropriate this morning to talk a little bit about the Scottish philosopher David Hume. For those of you that are at the conference in person, I think this particular statue is a few hundred feet from the building you're sitting in. David Hume in the 1700s sat down to look inside himself for self, for this unitary, unchanging res cogitans, which René Descartes had proposed 100 years ago when he stated, "I think, therefore I am." Where is this I? Where is this self? For Hume, he felt that his search was a failure. He did not find this unitary nugget of self. What he found instead was this constant flux, this constant change. And Hume said, he wrote that when he looked inside, he stumbled on particular perceptions, one particular perception or another: heat, cold, light or shade, love or hatred, pain or pleasure. He could never catch this unchanging kernel of self at any time. There was always just a flicker of perceptions. These perceptions succeeded each other with an inconceivable rapidity, and they seemed to be in perpetual flux. So this is what most of us see in modern neuroscience today. Of course, when we image the brain, we do see very complex dynamics unfolding over different timescales and complex, rich physiological change over timescales. What I propose, and one of the research thrusts in my group, is to try and exploit, first of all, create this rich inner lives in our soft robots or our biological robots, otherwise known as the xenobots. We try and create machines that have rich inner mental lives and physiological lives. And it may be that being able to grapple with constant internal change may, in essence, pre-train the machine to grapple with external change unfolding over different timescales. So I want to talk specifically about that today and focusing on something that Hume noted in the 1700s, which is this rapidity. If you think about your own inner mental life, things seem to flash before your inner eye very, very quickly. So I'm going to focus particularly on high frequency change. Okay. I've worked in sim to real, and I've worked with lots of software and simulation packages over the years. Actually, gosh, it's been 20 years now. If you scan from upper left towards the bottom right, my group has worked on rigid robots in the past, soft robotics these days, and in the bottom row you'll see some snapshots from some of our sim to real work on biological robots which you'll hear a little bit more about at this conference. But what I want to focus on today is the video you see in the bottom right, which is some recent and emerging work with my PhD student at TUSA Parsa. Corey O'Hearn, Mark Shattuck, and Rebecca Kramer-Botiglio at Yale. So what were you looking at? What you were looking at is what's known as a granular metamaterial. This is a metamaterial, as the name implies, that are made up of small grains or particles. In this case, you're looking at a relatively simple system with macro scale particles. Each one of these hockey pucks is about a centimeter across. And in each of these three one-dimensional granular metamaterials, there's an oscillatory force that's being applied from the left-hand side. And you can see that even in this simple arrangement, 1D arrangement, where each of the particles has exactly the same material properties, mass, friction, and so on, you get interesting vibrational dynamics, some of which are very high frequency. You'll notice, for example, that this forced oscillatory signal is amplified at some parts of the material and suppressed at other parts of the material. In this case, we're using a home-rolled simulator to simulate each of these three metamaterials. Why might we want to simulate or use granular metamaterials? Turns out that they may be of particular use in soft robotics. By vibrating a granular metamaterial, you can propagate force and or vibration through the materials. If we make soft robots out of different kinds of granular metamaterials, we can create rich vibrational properties that unfold over different timescales that might allow us to exhibit different kinds of gaits based on vibration or other interesting behaviors. As Rebecca and Corey have demonstrated in previous work, you can design granular metamaterials that act as an acoustic cloak. And we've just been awarded a National Science Foundation grant to look into reconfigurable granular metamaterials, where you can supply a signal to the material itself, reconfigure the shape of the grains, and therefore change the bulk property of the material, which might allow you to, again, create interesting behaviors if you make a soft robot out of these materials. So you're looking at a 2D granular metamaterial here. We have two particles, the green and the blue, that we can vibrate. And what I'm going to show you in the experiment today is designing a material to alter the transformation from input vibrations supplied at the green and blue particle and reading out vibrations that occur at the output particle, the red particle. Okay, so here's a particular granular metamaterial. In this case, the dark particles are going to represent stiff particles and the light gray particles are going to represent soft, pliant particles. It turns out that if you combine stiff and soft particles in just the right way, you can create a computational granular metamaterial. Again, if we consider the green and blue particles, we can encode bits as either a zero amplitude, representing zeros, and we can represent a 1 as a non-zero amplitude vibrational frequency. And we can tune this material so that if you supply, for example, two vibrations at both the green and the blue particle, you get a vibration at the red particle, and in the other three cases, the input vibration is snuffed out, and you can in effect create an AND gate using a granular metamaterial. Turns out this is a non-trivial problem. The previous speaker was just talking about optimization. In our case, we use an evolutionary algorithm where we evolve populations of granular metamaterials, which are different combinations of stiff and soft particles. And the fitness function, or the objective function applied to each material, is how much andness does it exhibit? How close does it produce this vibrational behavior under these four conditions? We usually start with random materials and optimize this against this fitness function, and we get granular metamaterials that act increasingly like an AND gate. More and more output frequency in just this fourth case, and more suppression of the input frequency in the other three cases. In this work, we actually took this one step further, and instead of evolving our computational metamaterials against just one objective, we evolved each material against two objectives, which is how well did it act as an AND gate at a chosen low frequency. We chose a different high frequency signal and asked how the same material exhibited a different logical transformation. How much did it act as an exclusive OR gate? When we do this, we can evolve a Pareto front of different materials. So each point, each dot in this cartoon figure here represents a given material. Here's the one up here, which is very good at acting as an AND gate at low frequency and very poor at acting as an exclusive OR gate at the high frequency. And at the other extreme of this Pareto front, we have a different material, a different combination of stiff and soft particles that acts very much like an exclusive OR gate at a high frequency and acts very poorly as an AND gate at the low frequency. Here is this actual material that was discovered. Again, you can see here we can supply neither one or both of the input particles with a high frequency signal. And we're looking for materials that output the same high frequency signal in just the second and the third case. What's particularly interesting to me, at least, about this work is what we find at the knee of the Pareto front. We can find particular materials like this one here, which acts as both an AND gate and an exclusive OR gate simultaneously. How does this work? Again, we're going to supply input vibrations to the green and blue particle, but we're going to represent, when we input a 1, we're going to multiplex or combine the two different frequencies to produce a combined signal, a multiplexed signal. When we look at the output particle, the red particle, we're going to look again that it acts as an XOR gate at high frequencies, which it does. In the second and third case, we recover that high frequency signal. And at the low frequency, it's still acting as an AND gate. We have a lack of that low frequency signal in the first three cases, and in the fourth case, we see that low frequency signal. So here's my little cartoon here of an AND XOR gate. I find this particularly interesting. Again, as we move forward in soft robotics and material science, if we manipulate materials in interesting ways, we can get them to act in very non-intuitive ways. In this case, we have a particular material that is providing computational superposition without recourse to quantum effects. You're getting it to compute two different functions in the same place, the red particle, at the same time. Not only do you have this computational superposition, but again, these are actual mechanical vibrations, so you also have force propagation. And so in this case, we could exploit this as an actuator or possibly as a sensor, because again, it is transforming incoming vibrations. We have a material here which is acting as a computational component. It could act as an actuation component and could act as a sensing component, all in the same place at the same time. I've got a couple minutes left, so let me just dive in and show you exactly how this process works. Here's our AND XOR gate here. We're supplying, I'm going to show you how this material behaves in the time domain in the right panel and the frequency domain in the left panel here. In this case, we're supplying 0, 0. We are not vibrating either of the two input ports, and there is no red signal. There's obviously no vibration at the red particle. In this case, the next case here, this is input 0, 1. We're supplying no vibration at the green particle. We're supplying a low frequency vibration. We're vibrating the red particle, the blue particle at a low frequency. And we can see the red particle start to respond, but given the behavior of this material, the bulk material collectively snuffs out the vibration or suppresses vibration at the red output particle. And in the frequency domain, we can see there's very, very negligible power at the red particle. In the case of 1, 0, we vibrate the green particle and do not vibrate the blue particle. We see a little bit of response again, but it's relatively negligible at the red particle. When we vibrate both the green and the blue particle, we get considerable power at the output particle. So here's the andness. We get 0, 0, almost 0, and 1 at the red particle. Exact same material. We're now going to vibrate the blue particle at a higher frequency, at 10 hertz rather than 7 hertz. And we get, in this case, a response at 10 hertz, which is what we want for the XOR gate. We vibrate the green particle, but not the blue particle. This is inputting 1, 0. We get 1 at the high frequency here. We get a response back. And again, when we vibrate both input particles at the higher frequency, the collective bulk property of the material collectively suppresses the output vibration. Okay. Just sort of a snapshot of some of the stuff that we're working on, which I find particularly interesting. This is, again, combining dynamics that occur at very high frequency and at slightly different frequencies. Not necessarily high frequency, but often higher frequency than we're dealing with in soft robotics. As I mentioned, pulling back, I think the challenge here is creating software systems that can simulate and exploit dynamics across very different timescales. Tackle the sim to real problem, figure out how to move those exploitations into physical properties and exploit them in the real world with our real soft robots. I'll finish up here just by thanking Tusa Parsa, my PhD student, who did all the real work here. And as I mentioned, we're just starting in on this funded project with our colleagues at Yale, Rebecca Kramer-Botiglio and Corey O'Hearn and Mark Shattuck at the City University of New York. And with that, I will conclude and take any questions if I have time. Thank you very much.